everyone. Before we get started on two sample t-tests, I wanted to bring back to mind what confidence intervals and hypothesis tests are really doing. So first, confidence intervals. Remember, the whole point of inference is to learn something about the population. So confidence intervals are one method we have to do that. Let's say we're back in the olden days when there was an NCAA basketball tournament, March Madness. And we want to know the percent of full-time workers who spend at least an hour of their day on March Madness activities. Well, we don't have access to all full-time workers. So if we want to know the percent of all full-time workers who are spending at least an hour on March Madness activities, we don't know. We don't know if it's 25%, 50%, 75%. All we know is it's somewhere between 0 and 100%. The percent of all full-time workers who are spending at least an hour of their day on March Madness activities in the olden days. But we want to know what that is. So what we're going to do is we're going to take a sample to get an estimate of what that true percent of all workers is. And according to one study, 56% of full-time workers spent at least an hour of their day, their work day, on March Madness activities. So that is an estimate, a sample estimate, we call that p-hat, of the truth in the population, the percent of all full-time workers who spend at least an hour of their day on March Madness activities. But we know if we took a different sample of workers, we would get a different sample percent. It wouldn't be exactly 56%, it'd be above that or below that. And so we add this cushion, the margin of error. And in this case, the margin of error was 4%. We think that that 56% is within 4% of the true percent in the population of all full-time workers who are spending at least an hour a day on March Madness activities. So we subtract 4 and we add 4, and we think that the true percent of all full-time workers, we don't know what it is, somewhere between 0 and 100%, but based on our sample, we think that the truth of all full-time workers who are spending in normal days at least an hour of their workday on March Madness activities is somewhere between 52 and 62%. Now there's a variety of things that affect the width of that, the sample size. If we increase our sample size, we have more precision, so this will be narrower. This is a 95% confidence interval, so we're not 100% sure that we've caught the true percent of all workers who spend at least an hour of their day on March Madness activities, but we're 95% sure. If we wanted to be more confident of catching the truth, we would need a wider interval. So it would be maybe, 51 to 61 or something like that. So if we want to be 99% confident, then we would need a wider interval, and that also affects the width. This margin of error, the 4%, the percent how close we think we are to the truth, only includes one kind of error, sampling error, the idea that this percent is going to be off from the truth by a random amount. It could be a little bit high, it could be a little bit low, but we're not off systematically in any direction. So this 4% does not include things like non-response, undercoverage, response bias. Maybe people are lying, right? This 4% would not include people who are the percent of people who are lying about spending at least an hour of their day on March Madness activities. So really this is an optimistic best world scenario, but it's our best guess and only guess at the truth in the population of all people who are spending at least an hour a day on March Madness activities. Okay, then hypothesis testing. Hypothesis testing is still when we're trying to learn the truth about the population, but now we're going to make a claim about what's true in the population and then collect a sample and see if we think that's reasonable or not. So let's say that there's an ad that claims that 7 out of 10 US doctors recommend aspirin for their patients with a headache. That seems high to us, so we take a sample and we want to see if the percent is 70%, if we have enough evidence to think that that might be true, or if we think that actually is less than that. So the population is all US doctors, and then the parameter, the thing we're interested in measuring, is the percent of all US doctors who recommend aspirin for a headache. if it's true that 70% of doctors recommend aspirin for a headache, if we took a sample of 100 doctors, so our claim is that 70% of doctors recommend aspirin for a headache. We wonder if it's less than that, So that's our claim about what's true in the population. P is the percent in the population of all doctors who recommend aspirin. We take a sample of, say, 100, and let's say that 61 doctors recommend aspirin. So our sample percent is 61 out of 100, 0.61. And our hypothesized percent is 0.70. So we collect sample data, and then we would compute a test statistic, seeing how far is 61% from 70% relative to the standard error. And then we get to the p-value. The p-value tells us if this is true, how often are we going to see 61 doctors or 61% in a sample recommending aspirin? Well, as you can imagine, if our sample percent is close to 70%, our p-value is going to be higher. There's a higher probability of seeing 69 doctors recommending aspirin when the truth is 70%, than there is a chance of seeing 61 doctors recommending aspirin. And that's the case. I computed a few p-values for us. So if 69 doctors recommended aspirin, when the truth is that 70% recommend aspirin, so we would expect 70 and we actually see 69, the p-value is 0.4136. So when it's true that 70% of doctors recommend aspirin, in a sample of 100, we'd see 69 doctors very close to 70, 69 or fewer, we'd see that more than 40% of the time just by chance, which is not surprising, right? We'd expect to see this often if this is true. If we drop down to 67 doctors, well, now we're farther away from 70% of doctors recommending aspirin, so the p-value drops. Now our p-value, if we have 67 doctors, is 0.2563. So if the truth is that 70% of doctors recommend aspirin for a headache, then how often would we see 67 doctors instead of the 70? 67 doctors or fewer recommending aspirin? Well, about a quarter of the time. So less often will we see 67 doctors recommending aspirin when the truth is 70% than we would 69. We go down to 65. Our p-value is 0.1376. If we go up down to 63, our p-value is 0.0633. So the further we get away from 70 doctors recommending aspirin, or 70% of our 100 doctors, the less likely it is to see such a thing when this is true. And if we have only 61 doctors recommending aspirin out of a sample of 100, well, then our p-value is only, let's see, 0.0248. So if the truth is that 70% of doctors recommend aspirin, we'd expect 70 out of 100 in a sample of 100 to recommend aspirin. How often would we see only 61? About 2.5% of the time. So it'd be very surprising. It'd be, well, quite surprising if this is the truth, to see only 61 doctors or fewer recommending aspirin. And so since the results are surprising, we're going to reject our null hypothesis that 70% of doctors recommend aspirin and believe it's something less than that. So we make a claim about what's true in the population, we collect sample data, and then we see if our sample results are surprising, if the null is true. In this case, our sample results were surprising. We'd only see them 2.5% of the time when this is true, and therefore we reject the null as unlikely, and we believe the alternate. So a few comments on p-values from the American Statistical Association. that journals too often decide which articles are worthy of publication by whether or not they include statistically significant results. Remember, statistically significant means p is less than or equal to alpha. So in the past, they've mixed up the idea of practical importance versus statistical significance. That they assumed just because it was statistically significant that it was practically important. That is not true. So hopefully they're changing their ways. Second, p-values do not tell you if your null hypothesis is correct. They simply tell us how likely our sample results are if the null hypothesis is correct. So this tells us how often we're going to see a sample percent of 61% if this is true. So it doesn't tell us if this is true or not. It tells us how often we're going to see this when this is true. P-values don't tell us whether or not our results are important in a practical sense. That's the problem that the journals were making. And then, of course, p-values are just one of many ways that people should look at data. That there got to be too much of an emphasis on p-values and not enough emphasis on describing the data, doing graphs of the data, and thinking about all those other things. So confidence intervals, hypothesis testing are two methods of inference. Confidence intervals estimate the truth in the population, start with a sample value, and then add and subtract the margin of error, how close we think our sample is to the truth. Confidence or hypothesis testing, we're making a claim about what's true in the population. We collect a sample, and then the p-value tells us how surprising that sample would be if the null is true. If our sample is surprising, if it would be unexpected if the null is true, then we reject the null as untrue.